So welcome back to our second talk of today. So the second talk will be from Professor Michel Kinnaert from ULB. Now, Michel, I know him since 15 years now because he's the director of the SAS, of the department where I work in. I could say a lot of things about Michel, in the sense that, all these years I could appreciate really the huge amount of very interesting work that he has done in different fields. And on the other side, on the personal side, also the fantastic person he is. So I'm very happy to present him and to leave him the stage.
Thank you, Emanuele, for a nice introduction. So the title of my talk is some tips about the design of fault diagnosis system, and I will speak about two case studies. So to motivate fault diagnosis systems or health monitoring systems, here are just two examples of catastrophic failures. So wind turbines can be subject to fires. Here is an example. So these can have different causes, either electrical causes like short circuits or ignition of hydraulic oil. And that's the first example. Another example is the accident that took place on the Qantas flight from London to Sydney quite some time ago. And so what happened is that shortly after taking off from Singapore, the reactor was subject to severe damage, and the damage of this engine was investigated, and it was seen that it was caused by an excessive leak of oil, and despite the high leak of oil, it was undetected by the monitoring system of the airplane. So that brings me to the goal of and the motivation for the development of performance health monitoring or fault diagnosis system. So what we aim at is the early detection and localization of degradations in order to be able to achieve predictive maintenance. So a synonymous that I will use for localization is isolation, and the degradations will be also called faults here. And I will give you some examples of faults later on. So the objective is that if we have a state of health indicator of our system, we can perform remedial actions before these catastrophic failures occur. And it also allows limiting the maintenance costs because predictive maintenance will typically be much less costly than corrective or preventive maintenance. It also allows us to keep nominal performance levels for our process or device, and so probably save energy or avoid possible environmental impacts, negative environmental impact. And also we are able to avoid costly unexpected shutdowns. So what are some examples of faults? Here are a few possibilities: sensor bias or drift, abnormal friction in gears and bearings, abnormal backlash, intern-turn short circuits in electric motors windings. This can be due to the degradation of the insulation, a leak in a tank or a pipe, battery overheating due to increased internal resistance, and so on and so on. So a typical fault diagnosis system is structured in the way presented here. So here you have on the top the supervised system, which can be an electric motor, a wind turbine, and so on. And typically, this model is driven by some known inputs, which are the comments that you are sending to the actuators. And you have also a series of sensors that equip the device, and these provide what I call here measured outputs. This system is also subject to disturbances. If you think of a car, you will have wind gusts that can affect the speed of the car, or you will have a difference in the slope of the road. These are disturbances, so unknown, unmeasured signal that affect the behavior of your system. And the faults are also unknown. And so what we want to achieve is being able to detect and determine when the behavior of our system is not anymore normal from what is available, namely the known inputs and the measured outputs. And so the diagnostic system, which is what is here below, is made of typically two parts. The residual generator. So a residual is simply a fault indicator. It's a signal that will nominally be close to zero, and that will take significantly non-zero values upon occurrence of a fault. And then you have the decision system. The decision system will analyze the pattern of zero and non-zero residuals, and from then decide which is the most likely fault and possibly estimate a fault magnitude. So I will illustrate through two case studies some issues in the design of our diagnosis system. And I will in particular show you that with quite simple models, we can already achieve quite effective results. So the first case study is the monitoring of electromechanical actuators for aerospace and aeronautical applications. And this is ongoing work with Louise Massager. We are working in collaboration with SAPCA, and we have a specialist in electric motors, Geoffrey Postal, from the BIS department, who also give us some help. So what is the motivation? Well, we are looking at two types of applications. One is the case of reusable launchers or simply launchers. So the orientation of the nozzle in those launchers and for the future reusable launchers, the deployment of the legs of the launcher, these things are actuated by these electromechanical actuators, which we denote in short EMAs. And of course, we have to ensure the proper reliability of these actuators, and to ensure this, we monitor the state of health of these actuators through the flight, and also for reusable launchers in between flight. But we have to evaluate the state of health of these actuators without dismantling them and putting them on test experimental setups. And we have to leave them in place and from the available data deduce what is the state of health of these actuators. Another application is the movement towards more electric aircrafts. Presently or formerly, a lot of primary control surfaces of the airplanes were equipped and actuated by hydraulic actuators. And the trend is to move from these hydraulic actuators to electromechanical actuators. It has several advantages. The removal of the hydraulic circuits limits the weight of the plane. It also avoids using hydraulic fluids which are far from nice from the environmental perspective. So these are two main issues, and that's why the movement is in that direction. But to equip such critical control surfaces, these EMAs must be equipped or must be equipped with health monitoring system to guarantee the appropriate level of reliability. And so that's a second motivation for the use of such actuators. So looking a bit more carefully at these electromechanical actuators, here is the way they are composed. So they have mostly an electric motor, which is a permanent magnet synchronous motor in the case we will consider. And this motor is driving a gearbox and a ball screw mechanism that induces this movement of the rod here. There is a suitable power electronics that ensures the control of the motor. So in here we will focus on electrical and sensor faults, and one of the difficulties is that we are working in closed loop here, so that the impact of the faults is more difficult to understand, at least from the intuitive point of view. So I will not bother you too much with electric motors, but just to tell you that we consider a star-connected with motor with insulated neutral point. And we consider a situation where a sinusoidal flux is induced by the permanent magnets of the rotor. And so one of the sort of faults that we will consider is inter-turn short circuits between within a coil. So that's due to the fact that the winding is made of turns, and the coil is surrounded by an insulator, but this insulator can be destroyed as time evolves, and that causes then short circuits between some turns of the coil. Another possible fault is the increase of the resistance of a coil due to the fact that when there is an overheating, the section of the coil could decrease. So what is the typical pattern of the current within such a machine? Well, in healthy situation, you have actually three-phase balanced three-phase signals, and that's what you can see here. So all currents have the same magnitude, and they are shifted apart by 120 degrees. But when there is a fault, and here I consider especially exaggerated fault levels in such a way that you see what is the impact of the fault on the signals. These signals are generated from a digital twin of our EMA. So when there is inter-turn faults, and 10% of the coil is subject to such faults, you get this stored signal. And this is what you get when there is an increase in the phase resistance. And so what you see is that the magnitude of the three signals is not anymore the same on the one hand. And on the other hand, given the properties of the motor that I have told you, the sum of the three currents must still be equal to 0. And to achieve this, there is a phase shift which is not anymore equal to 120 degrees between these different signals. If you look now at sensor faults, we consider here two kind of faults. So a change in gain of the sensors or an offset in one of the sensors. And due again to the control scheme, these faults affect all three current measurements. And what you see here again is that a change in gain means that the amplitude of the different measurements is not anymore the same. And an offset induces a change in the mean of the currents. But in this case, the sum of the currents of the measurements is not anymore equal to 0. What is still equal to 0 is the sum of the actual currents. But the measurements are not the actual currents due to the sensor faults. So we see that we can actually model these current signals independently without the need to model the motor itself. And that's what we are going to do to try to achieve fault diagnosis. The advantage of doing so is that we will not need to know the parameters, the resistance, the inductance of the motor, which can be subject to temperature changes. And so this brings uncertainty. Here we stick to the measurement of the current. So a three-phase, balanced three-phase system can be represented in this way. And you can show that these three sine waves can be actually generated by a simple two-state system, so a system of two linear differential equations, which is an oscillator. This oscillator will generate in its states a sine wave and a cosine. And if you add up this sine and this cosine and multiply them by proper values, you get this balanced three-phase signal. So this is for the healthy situation. For the faulty situation, what happens is that the signal magnitudes are different and you introduce a phase shift. So if we take as reference the first signal here, we can actually introduce four variables, which are MB over MA, MC over MA, and the respective phase shift with respect to phase A here. So that makes four unknowns. But if we consider first the case where we have interturn short circuits or increase in resistance, we have seen that Kirchhoff's laws then must hold. And if Kirchhoff's laws hold, that's introducing an extra constraint, which means that these four variables can actually be expressed in terms of two independent parameters, which we denote psi1 and psi2 here. And so that means that in the case of winding faults, our model takes this form where the only thing that changes is the equation that generates the three currents from the states. And this is a simple diagonal matrix where we have these two unknown parameters, and the C matrix is becoming C tilde, so this C matrix is changed a bit as well. In the faulty case where we have sensor faults, well, we have seen that bias or an offset induces a change in the mean, which we can characterize in this way, so simply an additive constant in each line of my equation that gives the current. And the gain change is simply modeled by this diagonal matrix, which again will multiply each measured output. So notice that these faulty models also contain the healthy models for some values of psi1 and psi2. Namely, here, if I take psi1 and psi2 equal to 1, I will recover the healthy model here as well. And here, if I take them equal to 0, I will recover the model as well, the healthy model as well. So we have to keep that in mind for a later stage. So this brings us to the design of the online fault diagnosis system. So the equations that I've just written down, I can formalize them a bit more and discretize them. So as we have seen, in the faulty case, there are some parameters that are introduced here. These parameters do not change very fast, and so we can consider that somehow when we have recorded data, the parameters are quasi-constant with respect to the dynamics of the sine wave that we are considering. And so that's what we are saying here. Our parameters are quasi-constant, but they are uncertain, and this is represented by adding noises here. This is the standard form for this output equation here. And what we have also introduced is that the current signals are subject to noise, and we have represented noise, measurement noise here by V. So these noises can be characterized by the so-called covariance matrix indicated here. And so now the problem is to determine in what situation our motor is working. And so to this end, we want to estimate the parameters here and determine in what sort of model, what is the most likely model among the models we have been considering previously. So we have this model, this model, this model, plus the healthy model, which is the one that fits the data best. And so to achieve this goal, we will resort to what is classical in control engineering, namely state observers. And here, as we are in a stochastic framework, we will resort to what is called a Kalman filter. A Kalman filter, if I had a linear model, would yield the minimum variance estimator. Here, as I'm in a nonlinear case, I look for an approximate solution, which is given by the extended Kalman filter. So this extended Kalman filter will take as input, something I forgot to say up to now, is that I assume that my motor is operating at constant speed. And omega E here is what is called the electrical speed of the motor. It's linked to the mechanical speed of the motor thanks to the number of pole pairs of my motor, but this is a bit technical. So I assume that this electrical speed is constant, otherwise I would not have current that keep having the same frequency. And for the application that I consider, there are at least some times where such an operating mode is encountered. So I have my speed of my motor, I have my measurement of the current, and what I will generate is thus an estimate of the unknown parameters in my model. But I will also have an indicator of the quality of my estimate through what is called the innovation signal. So the innovation signal is simply the difference between the measurements and the prediction of my measurements from the previous data. So this is the prediction of my current at time k, given all the available measurements up to time k minus 1. And so it's called innovation because it's the new information brought by the measurements k. And so it turns out that these quantities have specific statistical properties that are estimated by the Kalman filter through what is called the covariance matrix of the innovation signal and the covariance matrix of the parameter estimate. And so what we will do is run different state estimators, one for each specific situation. So we will have one Kalman filter for the healthy model and 3 extended Kalman filter, or here it's dual extended Kalman filter, but I will not enter into the subtleties, for each of the type of faults. And then from the innovation, we are able to determine what is the relative likelihood of each model. And so, for instance, in this case, we are starting from a healthy situation and the fault in the, so we are initializing our likelihood to the healthy case. And then we are seeing that the likelihood for the winding fault is appearing because the data correspond to a winding fault. And we can check from the parameter estimates that indeed the parameter estimate and including surrounded by the confidence interval. So these parameter estimates do not include the healthy situation. So we can confirm indeed that in this example, we have a winding fault. So that's the principle of the fault diagnosis system we are looking at for the moment. And some preliminary results have been obtained on synthetic data, where 16 scenarios have been considered. The healthy case, different in-turn short-circuit faults with some, here you see that we have a much lower level of short-circuited turns. We have also considered a situation which I have not spoken about yet. It's interface short faults. So rise in phase resistance, gain change, and offset in the current sensors. And you see here some results depending on the signal-to-noise ratio of our current signals. You have here the probability of misdetection, PMD. The probability of false alarm, so then an alarm is generated while the motor is in healthy case. And the probability of misclassification, so that's a situation where one fault is considered, the identified fault is not the correct one. So you see that the performance seems to be reasonable at this stage. And these results are obtained by performing 100 realizations for each of the 16 scenarios with different noise. So what changes is the noise realization. So what's the difference between the synthetic case and the actual signals? Well, when you look at actual current measurements, and Geoffrey Postal gave us some of them, what happens is that you just don't have one sine wave. Okay, these signals are made of several harmonics, and here is actually the Fourier transform of one such signal. And you can see that there is actually a fundamental here around 50 Hertz. And then you see harmonic 3, 5, 7, and 11 here, plus some other frequencies that are linked to nonlinear phenomena in the motor. So how can we cope with that? Well, the method I've just presented can be extended by just adding 2 more states per harmonics and modifying the output equation appropriately, but the global methodology carries over. And this is actually what the currents look like. So you see that you don't have any more this very pure sine wave. So here is the first results obtained by Louise on these experimental data. These data are for the moment obtained in open loop, not in closed loop, so we still have some work to do. And this is what we call the confusion matrix. So what you have here is the true class, so we distinguish healthy motor fault, sensor gain fault. We have not considered sensor offset here. And here you have the decision on, the decision taken by the diagnosis system. And you see that, so here we consider all the data that Geoffrey has provided us with. And what he did is he modified the load of the motor so that we have different signal-to-noise ratios in our data. And you see that if we consider all signals-to-noise ratio, we get some indeed erroneous decisions. Like for instance here, you have 13 situations where, despite the fact that you have a motor fault, it's declared to be healthy. So this is a missed detection. You have also here 1 false alarm. But you see that in the majority of the cases, a correct decision is taken. If you have increased signal-to-noise ratio, you have even better results. So what is the main message to take from this first example? By analyzing and understanding the effect of the faults on the measurements, we were able to use simple signal models and to avoid using a model of the motor for which we need to estimate parameters that could be varying with temperature, for instance. So ongoing work is to look at real data in closed loop, systematic tuning of the extended Kalman filter, and possibly also constrained parameter estimation, because indeed here we have to go in these 2 steps where we check that the parameter estimate does not embed the healthy case. Another approach could be to make sure that this estimator will never estimate the healthy case by enforcing that the parameters stick to some situation where the model is faulty. So that was for my first case study. So please stop me if I'm too long. The second part of my talk will be dedicated to wind turbine monitoring. And so I will have 3 sections, but the last 2 are very short. So I will start with the issue of loss of performance detection, and then I will go to generator cooling system monitoring and give a few hints on a global monitoring system. So here is a very quick look at what a wind turbine looks like. So you have here the 3 blades of your turbine. You have what is called the low-speed shaft that drives a gearbox. You have the high-speed shaft that is connected to the generator producing electricity. Now what I want to stress here are the 3 types of actuation mechanism on this wind turbine, 3 main types. So you have the pitch. So the pitch allows you to orientate the blades. You have the yaw drive. The yaw drive is here schematically indicated by this. So it allows you to orientate the nacelle of your turbine in such a way that normally the nacelle should face the wind to extract the most of energy from the wind. And finally, you have the generator torque. So you can somehow try, thanks to the power electronics, control the torque of the generator in such a way that you control the rotational speed of the generator and the wind turbine. And the reason you do this is explained through this graph, which is called the power curve of the wind turbine. So here you have on the y-axis the power produced by the wind turbine, and on the x-axis the wind speed. And you see that there are actually 4 zones. Below a certain wind velocity, the energy in the wind is not sufficient to be able to produce electricity. So this minimum wind speed is called the cut-in wind speed. And then you have what is called the maximum power point tracking zone, which is this zone. And on onshore wind turbine, this is the zone where the turbine operates most often. So in this zone, you are actually controlling the speed of the wind turbine in such a way that you extract the most energy from the wind. That's why it's called maximum power point tracking. Then you reach the rated power, which is called Pn here for nominal, at the nominal velocity. And finally, and this depends on the wind turbine, this 4th zone, you don't have it necessarily. You have sometimes what is called the soft storm transition zone, where above a certain wind speed, the power generated is decreased before cut off, and so stopping the turbine when there is just too much wind. So this is the steady state characteristic somehow of our wind turbine. And this is what you find in the data sheet of the wind turbine. But in practice, all you have available are data points, and these data points come from SCADA data. And these SCADA data are typically 10 minutes average of notably the power, the wind speed, and a series of other signals like the pitch signal and so on. So here we will choose to try to monitor our wind turbines using this power curve as we expect, so for a given average wind speed to produce a given average power. Now, what should we take care of? Well, one first thing is that the produced power, well, the power, available in the wind for a given wind speed also depends on the air density rho here, and A here is the area swept by the blades. So we have to normalize our power curve by rho properly in such a way that we can compare the power produced in different days where the density is different. So there are different ways to do that. You must also account for the way the wind turbine is controlled. We have chosen this one, and just for the sake of clarity here, what you just need to keep in mind is that the normalized values are indicated by this 0 exponent here. Now, when you have normalized the data, here is what you can get when you try to use SCADA data and plot the power curve. So you see that besides the curve that you have in the data sheet, you have some additional points. You have some dispersions because you are doing also 10-minute average. But you have clearly situations where, for instance, here the wind turbine is at standstill while it could produce. Mainly, it could be in maintenance, for instance. You have situations where it is operating in power derating mode. That means that the grids cannot accept all the power available in the wind, and so the wind turbine is derated. And you have points like 3, for instance, which corresponds to high-speed startup. So these operating conditions are different from normal operation, and so we should discard them to have a monitoring system that covers most of the operating cases. And what is our aim? Our aim is to detect certain malfunction in our wind turbine. A possible malfunction is what we call yaw misalignment. In yaw misalignment, what happens is that the nacelle is not facing the wind anymore. There is a misalignment, so an angle here, gamma, which is non-zero. And this yaw misalignment induces a reduction in the produced power of the turbine. To show this, this is an experimental curve and the little triangles here obtained for a 75 kilowatt wind turbine, experimental wind turbine. And so you see that indeed with a non-zero yaw angle, the produced power is decreased. So what is the problem we aim to solve? We want to monitor the performance of the wind turbine and detect degradations such as yaw misalignment, for instance. And we need to account for the outliers in the design. So we will operate in the following 2 steps. First, residual generation, then decision system, and we will end up with a validation on real data. So actually, these are already real data, but we will validate with real data corresponding to 40 operation. So again, we will try to use very simple models. And as we are control engineers, if you flip the power curve here, and keep in mind that we are essentially interested in this operating zone, which is the zone 2, which corresponds to the maximum power point tracking zone. So if you flip this curve, you see a curve which is very similar to the step response of a typical second-order model. And so that's what we have been using to parameterize the curve linking the normalized power to the normalized wind speed. And so now we must get rid of all these outliers. To do this, in statistics, it's classical to use iterative reweighted least squares. That means that initially one will solve a problem, a least squares problem. So we will sum here over all the samples the square of the errors between the measured power and the estimated power from the model. And at first, we will start with a weight which is equal to 1. And then we will compute for each data point the error. And we will introduce a weight which has this shape here. So when the error is above a certain threshold, the corresponding data in the optimization problem is weighted less. And we iterate the determination of the parameters, so the solution of this optimization problem, until there is a small difference between 2 successive iterations. And this is the type of result we get. So you see that the weight corresponds to the color map here. So you see that indeed the points that are weighted the most indeed correspond to our power curve, and the outliers have very low weight and do not significantly affect the parameters of our curve. Now we have our model of our power curve. Let's look at how well it fits when we are using actual wind turbine data. So we have used here wind turbine data coming from 2 wind farms that are called SPDM and CBAR respectively. And so you see that the errors match quite well a Laplace probability density function. So these are normalized histograms. And so we will characterize these modeling errors by Laplace distribution. And now the idea is to try to see what is the impact of a fault. And here, remember, we look at yaw misalignment. What is the impact of a fault on this error distribution? Can the distribution be used to characterize the presence of the fault or not? So here, as it's difficult to have faulty data on which we have sufficient control, we have used a realistic wind turbine simulator developed by NREL. It's called Aerodyne Fast, and we have simulated 10-degree yaw misalignment. And the blue dots corresponds to the faulty turbine, and you see that the deviation from the normal, the healthy turbine, essentially occur in zone 2, and in the fast storm, the soft storm transition zone. But as we are operating very seldom in this zone, we will discard it and focus on this zone. And this is the modeling error that is obtained upon occurrence of this yaw misalignment fault. So you see that there is a mean shift in the Laplace distribution, so that we could indeed detect a shift in the mean. In the healthy case, our Laplace distribution will have a mean very close to 0. In the faulty case, it will be shifted. And so our decision system can be based on the log likelihood ratio, or the likelihood ratio between the healthy and the faulty probability density functions. So more precisely, if you consider the modeling error, which we call R here for residual, or for a given time horizon, and if you consider that these samples are independent, you can easily compute the likelihood function in the presence of the fault and the absence of the fault. And a standard test consists in comparing this likelihood ratio to a threshold. And if the likelihood ratio is below the threshold, it's the healthy case that dominates. If it's above, it's the faulty case that dominates. And this threshold must be adjusted to ensure that the probability of false alarm is appropriate. And this is an example of what we obtained with real wind turbine data. So what you see here is the produced power of the turbine over the years. And here is the indicator. So notice that we built an indicator each time after a few weeks of data, because we must be able to reconstruct the power curve or to estimate the probability density function with sufficient precision. And you see that at some stage we cross actually the zero threshold here, which corresponds to the occurrence of a fault, and indeed a yaw malfunction was obtained at this stage. So a maintenance operation took place, and you see that our fault indicators falls back with two negative values, which then correspond indeed to, again, a healthy situation. So just a few more words, speaking about generator cooling system monitoring. So here we speak about the cooling system of the generator in a wind turbine. So this cooling system is actuated, or is made of fans. There is actually a series of 3 fans, and there are temperature sensors in the coils of the generator, and there are actually 3 coils and 3 temperature sensors. And what we have been able to show is that, again, using a very simple dynamic model, first order dynamic model actually, one for the cooling of the coils, so when the cooling system is operational, one for the heating of the coils when the cooling system is not operational, because this cooling system works in on-off mode. Well, when just keeping this very simple model and using, again, simple statistical tools, we were able to obtain a fault diagnosis system that has reasonable performance, or at least that has some interesting properties as compared to what the SCADA system of the wind farm is doing. So we have here a series of 43 wind turbines and data recorded over 3 years. And so what you see here with the yellow dots correspond to SCADA alarm. And the red dots correspond to work orders, so maintenance operations. And on the other hand, the new monitoring system that is based on the dynamic model is issuing a green information when the wind turbine is healthy. A red line means alarm, and a blue line means warning. And what you can see is that most SCADA alarms occur in autumn or late summer. Why? Well, because this is the period of the year where the temperatures are still reasonably high and there is significant wind. So if you have a monitoring system that just compares the measured temperature to a threshold, that's when it will be triggered. But as you can see, for instance, in here, our monitoring system has detected a fault way before the first alarm takes place. And this is simply due to the fact that it detects that the cooling dynamics is not what it should be, so that a fan is probably faulty already by then. And so that shows you that by using simple dynamic model, you can already anticipate failures compared to what you have in traditional SCADA system quite long in advance in some cases. So this said, I think that I have given you a few elements, a few components for diagnostic system. The way I would see a global for diagnostic system, for instance, for a wind turbine, would be to have a series of such blocks that I have presented you, preceded by a systematic measurement validation. And as some of these blocks might be sensitive to, the same faults, there is a need also for gathering the information issued by these blocks inside of a global fault diagnosis system. And the objective would be to have plug-and-play models that you could introduce here in place of these 3 dots, and that you could have some systematic way to adapt this global fault decision system without redesigning it completely once you add a new device. So in conclusion, I hope I have shown you that it's possible to use reasonably simple models in fault diagnosis. You must be careful when you have real data to clean them properly, but there are ways to clean such data reasonably easily. Statistical approaches give you the possibility to detect relatively small faults. And I believe that we should aim at modular structures for diagnosis system. And finally, I think we should also aim at diagnostic system that can be tuned with relatively few data. It's not possible to wait, for instance, that a wind farm has been operating for 1 year before being able to start monitoring it. So thank you for your attention, and I'm open to questions.
So I imagine there will be questions.
Thank you. Thank you very much for the very nice talk. So I was curious. I think that the main message of all these approaches is that we need to rely on a model in order to do fault detection. I guess modeling takes efforts. We need to develop them, tune them, and then refine them over time. I wonder if there is a view towards moving to a framework where we only use data, statistical framework or something along those lines, or if there is a strong view to remain on a model-based approach.
So I think it's what is model-based and what is not model-based is a real discussion. I mean, because here, as you can see, I have a model, but I have a model of a sine wave, which is a signal. So is it model-based? Is it data-based? That could be discussed. And so I think what I would like to stress is that, yes, we can use model, but we can go with very simple model if we analyze the problem sufficiently. And what we should aim at is using models or methods that are as little dependent as possible to the operating mode of the system or some specific parameters of the system. So, we should definitely be aware of what physical phenomena could influence our model or data in such a way that we can account for them or take extra measurement to take them into account. So that's, I guess what's important is to analyze the physics behind the device we are looking at and not just stick to the data. I don't know if I answered your question or not.
Thank you for the presentation. I was wondering what happens when you have multiple faults that are happening at the same time. Are you able to distinguish between them, or yeah?
Okay, so yeah, that's a bit tricky. We could, in the first case, for instance, have models that include the two phenomena together, for instance, a sensor fault and a bias fault, and possibly estimate both cases. The more parameter you have, the the more difficult it is to estimate them independently. So you must be careful. There are rare situations where you can really build indicators that will only be dependent on one fault and just one fault. And in that case, of course, it's possible to achieve simultaneous fault detection and localizations. But it's not very often the case in real applications. And so still having the possibility to detect and isolate multiple faults, it's also a trade-off between the complexity of the fault diagnosis system you are building and the possibility to achieve this goal. I think also that most often faults will occur not synchronously but progressively, and so we could still have benefit of having a fault diagnosis system that only take each fault at a time.
Thank you.
Other questions? If not, actually, I have one comment, because you said something very interesting in the previous question. That is, it's not a matter of data, it's not a matter of model, it's a matter of knowledge of the process we are playing with. Mm-hmm. So somehow, in classical control, there are plenty of papers that basically say, and plenty of people that have said for decades, give me the equations and my theory is general for whatever thing that is behind the equations. And then when you face reality, we have seen in your talk, we've also seen the talk of Dennis before, you must have a knowledge of the process you are controlling. Maybe this is also something that is true for everything that is data-based. One cannot think that the technique completely allows us to be independent from the knowledge of what we do.
Yes, I totally agree with you. I believe that well, we can, but if we can try to do something that does not exploit any physical knowledge. But I think the performance we will obtain with the end product, based on not knowing anything and discarding everything, will be much less ideal than what we can get if one exploits the physical insight that we have in the process. And for instance, here in the case that we have balanced signal, for instance, is a property that, if you take it into account, allows you to have much better performance than if you just discard that and start building robust observers. You will never get the same type of performance. So it's, for me, and that's why we are engineers. I mean, engineering is just exploiting physics and merging different fields. Otherwise, we are just too specialized. And I think when we start dealing with application, we must really also cooperate with the specialist of the applications to be able to exploit the most of it.
Other questions, comment? Well, then I will take the occasion to provoke a little bit another thing that was, again, a follow-up of something that Denis said, that is about instead the needs probably for engineering in general to have knowledge of dynamic system from the very beginning. Do you have the same feeling?
Definitely, yes. As you have seen, the dynamics here is everywhere. Okay, I have used a steady state characteristic for the wind turbine, but except from that, for the simple thermal process, we have used dynamics, and we have shown that taking into account dynamics makes a complete difference. And it's the same experience that we have encountered in many other applications. So I think dynamics is fundamental for control engineers, but more generally for any engineers. And indeed, I think it depends also on the training and the tradition. I would say that civil engineering and chemical engineering are traditionally disciplines in which the dynamics is not very much taught, while in some other engineering disciplines it's much more developed. So I guess it's also very culture dependent, but it's definitely very important to account for the dynamics, and that helps a lot for fault diagnosis also, because a fault induces a transient, so a fault necessarily is seen through dynamic phenomena.
Okay, so with this, I would thank again Michel. Thank you, Michel.